Our paper title is Digital Audio Watermarking for Protecting Audio Classification Datasets, and our article ID is ICEARS036. Our project aim is to embed a watermark into an audio signal so that we can get another audio signal out, we can get another signal output which have an embedded watermark in it. So this can be used for copyright protection and for security applications. Previous studies on audio watermarking technologies requires the actual sound of the watermarked audio to extract the information embedded in it. In our study, we proposed an audio watermarking framework to identify whether a deep learning based audio model is trained with the watermarked audio classification dataset or not by using only the classification results. Now, if we go into the detailed explanation of the audio watermarking, yes, recently a necessity has arisen for copyright protection of digital content against piracy. This audio watermarking is mainly used for the copyright protection against piracy attacks. Digital watermarking, the art of hiding information into the original audio signal, has been proposed as a potential solution to this problem. This mask should not degrade quality. That means this mark should not degrade audio quality in the sense this should not interfere any noise. We should get the output which is same as but with a watermark in it. The difference between the image classification and audio classification using deep learning is in the input features. In the case of image classification, the image itself is used as an input feature, whereas in audio classification a form of converted to time frequency representation is often used. That is, for example, if this is an image, it is used as the input for the classification, but whereas in audio it is different. If this is an audio signal, we have to convert it into time domain signal for further classification. The contribution of this paper is we propose an audio watermarking framework to protect audio classification datasets used in deep learning. And the second thing is we evaluate the usability of the proposed audio watermarking framework with the different datasets, input features, and audio classification models. If we go to the watermarking framework, public in this study we propose a method of making a dataset public after adding a watermark to a subset audio files in a subset of audio class. The approach is similar to the approach proposed in the study for image classification dataset protection. The method of determining whether the published dataset is used for training model is to add a watermark to a sound source of a class that is not watermarked and observe its result. And here if we see here, the time frequency representation depend on a variety of factors including window size, hop size, and whether a frequency filter is used. Here frequency filter in the sense the filter may be a kernel. Kernel is also a filter. Hop size in the sense the distance between the distance between the signals. And window size is nothing but the distance between the two signals. There are different types of windowing techniques like hamming window technique, Hanning window technique. We can use the window technique according to our need. If we see the problem statement, we can see that communications via internet has a greatly facilitated spread all over the media data for many years. It has accelerated the renowned issue of online piracy, obtain improper attempts to purposely corrupt the protected data and hence misuse it, illegal sharing of protected audio data. For example, we can protect our audio signal by embedding a watermark. If we embed a watermark while doing copyright, we can protect our audio signal. There are various methods exist for audio watermarking. For the first technique is time domain technique. Time domain technique. The initial audio signal segments that have been used for watermarking are now used. The least significant bit LSB method is an illustration of a time domain watermarking technique. The host signal's least significant bits includes the watermark when applying the LSB method. That is, we know about MSB and LSB. This technique is used here by taking various bits in it, like here 1 0 1 1 0 1, whereas this is LSB and this is MSB. This is one method, and the second method is the spectrum technique, whereas we use watermark data is given to a multiplexer to add, whereas here we give pseudo noise sequence PN sequence, and which is given to another adder where we give audio signal here, input audio signal, and we can get the watermarked output here. This is the second method. This is first method, time domain technique. And another technique is discrete wavelet transform technique, DWT. TWT. Another technique is discrete cosine transform, DCT. And another technique is DFT, discrete Fourier transform. It is coming to discrete cosine transform. It is employed to integrate data in the transform domain and contrasts from DFT in that it includes some DCT features such as officially given energy compression, and its coefficients contain actual values. Coming to discrete wavelet transform, the capability to identify the sound quality in the moment as well as the wavelet transformation property, the selection of various thresholds, but the fact that DWT requires fewer operations than DCT and DFT, because when maximum number of samples is available are now just a few advantages of using DWT on sound waves. These are some of the existing methods. Through this project, we propose a method for declaring an information available after a portion of audio recordings in a fraction of the audio class have one watermark applied. This procedure is related to the one suggested in the report for protecting processing data. We can see here class 1, class 2 up to class n, watermarked and not watermarked data. That is, we can take two statements. That is, one statement is if condition, if it is not watermarked. Second condition is else condition, that is watermarked. That is watermarked. And based on this condition, we can perform CNN here, convolution neural network. And for this also we can perform CNN, convolution neural network. Here, see, if you can see here, the audio signal is given, and the magnitude of the audio signal is derived using STFT. STFT means short term Fourier transform. And phase is not related with the magnitude, but while taking output we require phase condition. That's why we have taken a loop from the starting. Watermark is embedded to the magnitude, and using inverse short term Fourier transform we can get the watermarked audio output. The STFT procedure we can see in the coming slides. For we have to for this process, first we have to take an audio signal, and this audio signal is converted into spectrogram for analysis. We give the watermark to this spectrogram to get the watermarked audio, because converting an audio signal into spectrogram makes our process easy. The proposed method we can see CNN, convolution neural networks. It is nothing but if we take an image, it is divided into various pixels. Each box is called a pixel. We can take 2D. Here we use 2D convolution. Convolution in this is 2D convolution. For using 2D convolution, audio watermarking is done, and we use STFT. We use STFT to convert it into frequency at point we are getting high accuracy, we are making watermark there. First we convert the signal into frequency domain. At a point where we are getting high accuracy, there we are going to watermark. For that we can use a kernel which is called a filter. Previously we have seen that we need a filter. This kernel is multiplied. This kernel is multiplied with CNN, whereas kernel have some random values. Some random values. Applying kernel at every point of image, that is image matrices values. Final output we can get a featured map. From this final output we can get a featured map after multiplying CNN into kernel. From this we can pull out the maximum values called pooling. Pulling out the maximum values is called pooling. There we can apply our watermark. There are different layers like input layers, hidden layers, output layer, maximum pooling layer. There are so many layers in it. Hidden layers, it's layers in which we give the input to our model, is called a hidden input layer. The capacity factor such as Gaussian or softmax is then applied to in the output layer to interpret the output of each class into an accurately and completely for each class. This is after output layer, that is softmax layer. After output layer we get softmax layer. And there is also another way used to use CNN is a unit architecture which consists of two CNNs that are nearly mirror imaged and produces CNN with a U-shaped architecture. Units are commonly used in applications in which the output must be the same size as the input, which including segmentation and picture enhancement for each convolution layer. A gathering of detectors known as convolution kernels are available. Next we can go for padding. Padding in the sense multiplying. For example, we can take a signal and if we multiply with zeros, then it is called as padding. We can take a signal and we can multiply it with 1. This is called padding. We have another layers also like image input layer, convolution layer, related convolution, featured map, zero padding, dropout layer, maximum and average pooling layers, batch normalization layer, rectified linear unit layer. This we already discussed in the previous slide. Advantages and applications of the proposed method: copyright protection, vendor identification, evidence of proprietorship, validation of genuineness, content identification. Here we can see the implementation. Implementation is first we pre-allocate an STFT output array. Next, with the window length n is equals to FFT length, we take m is equals to length of W, that is whereas capital M is window length and n is FFT length. Now the next zero padding which is to be inserted. Next current offset in the input signal X. Assume m odd for simplicity. We assume m is odd for simplicity. M is in the sense m is window length. Extract a frame of input data. Apply window to the current frame. Next after applying window, next zero padding. We will use zero padding. Next STFT for frame m. We use short term Fourier transform from frame m. Advance in priority by hop size r. At last stage we have to take the advance in pointer by hop size r. STFT is nothing but if we take a signal, we will convert it into time domain. The name itself says it's a short term Fourier transform. Between every short terms we introduce a Fourier transform. We use it to watermark. We use very short terms. High sampling rate means high accuracy. So we are using very short terms. High accuracy. See here we can see the signal is divided into n sections. This signal is divided into n sections. Each time n points are taken where n is equal to the window length specified. The chosen window type is used to multiply the extracted data. We can use the window type of Hamming window type. Zeros will be padded on both sides of the window. If the window length is less than the size of the FFT length, FFT is computed on the FFT section. Next, moving the window according to the user specified overlap size and repeat steps 1 through 4 until the end of the input signal is reached. The window is implemented in zero centered, that is zero phase. The signal should have at least leading zeros for the implementation. Now, if you ask a question that why we are using only MATLAB, that is MATLAB compiler, we have by using MATLAB compiler, it has a standalone application, Excel add-in, Hadoop, high level, it is an high level language, interactive development environment. It is easily share your analysis with can easily share our analysis with others. We don't really need a formal background in signal processing to analyze the signal with MATLAB and signal processing toolbox. These are our end results. This is if condition, this is if condition, this is else condition. Choosing an option for classification, if you want to classify, if we choose classification, the classification of the signal will be performed directly, and if we choose watermark, then watermarking will be performed and then the classification is performed. Next we will get the spectrogram of the input audio. Whenever we choose classify, we have to select an audio signal from our system, then that audio signal is converted into the spectrogram. The above figure shows the figure 3 shows the training process as well as the training process of the input audio after insertion of watermark. Training of the convolution neural network for classification of audio watermarked and non-watermarked audio. Next, fourth one, the above figure shows the watermark is not inserted in the input audio and it is displayed with the help of the message box. If the watermark is not inserted, then it shows non-watermark. If it is inserted, then it shows watermark. After selecting the audio signal, it is converted into spectrogram signal. The next condition, we have to select the watermark. That is, we have to select an spectrogram signal which is saved in our PC. That spectrogram signal is applied to the audio signal. Then by multiplying both, we will get an watermarked output. Here see the above figure shows the training of the CNN for classification during the classification of watermarked output. During the watermarked output, it shows the classification. It's classified watermark. Previously we have got not watermark. Now we are getting watermark. That is because we are watermarked the signal. Before conclusion, we will evaluate the process. To do this, for evaluation, we selected 100 random sound sources from the classes without watermarking that were not used for training and inserted watermarks to them. We evaluated the accuracy with which our models classifies these sound sources into the watermarked class. The evaluation criteria is expressed as accuracy drop, and if we come to the conclusion, we proposed a noble watermarking framework with possible watermark for protecting audio classification datasets. A proposed watermark that embeds a specific pattern in the magnitude domain of time frequency representation was evaluated in various input features models and datasets. In addition, we will check the effectiveness of our proposed watermark with real-time sound classification models and watermark sound propagating through air. That's all.